Welcome, everyone. I'm excited to kick off today's presentation on calculus and analytical geometry. This is our first slide, so I'd like to briefly introduce the topic. We'll explore the fundamental concepts of calculus and how it connects with analytical geometry. Over the next few slides, we'll cover key ideas, applications, and some interesting insights into these fascinating fields. Let's get started. Now, as we reach the conclusion of our presentation, I want to briefly revisit what we've covered. We started with the basic concept of a derivative, understanding it as a fundamental tool in mathematics. Then, we explored how derivatives are applied in real life, from economics to biology, showing their practical importance. We also looked into how derivatives are used in physics to analyze motion and forces. Moving on, we discussed some key rules for differentiation, which help us compute derivatives efficiently. It's important to see how all these points connect, as derivatives are truly versatile and essential across various fields. Finally, I want to thank you for your attention and engagement throughout this journey into derivatives. Today, I want to talk about derivatives, which are a fundamental concept in calculus. We've explored their definition, understanding what derivatives actually represent and how they measure the rate of change. We also looked into the history of derivatives, seeing how they developed over time and their significance in the evolution of mathematics. Moreover, we discussed their real-life applications, from physics to economics, demonstrating how derivatives help us solve practical problems. Lastly, we examined how derivatives are applied across different sciences, highlighting their versatility and importance in advancing scientific understanding. All these points tie together to show how derivatives are not just abstract ideas, but powerful tools that influence many aspects of our world. Let's explore the concept of the derivative. The derivative of a function essentially measures how one variable changes instantly in relation to another. Think of it as the rate at which something is changing at a specific moment. Geometrically, this translates to the slope of the curve at a particular point, so the steeper the curve, the greater the rate of change. This idea is fundamental because it connects the concept of change with the shape of the graph itself. The process we use to find this derivative is called differentiation. It's a powerful tool that helps us analyze and understand the behavior of functions in a precise and meaningful way. Now, moving on to the history behind modern differentiation and derivatives. These concepts are usually credited to two brilliant mathematicians, Isaac Newton, who lived from 1643 to 1727, and Gottfried Leibniz, who lived from 1646 to 1716. Both of them independently developed the fundamental theorem of calculus during the 17th century. This theorem was a breakthrough because it linked differentiation and integration in a way that fundamentally changed how we compute areas and volumes. Their work really revolutionized the methods mathematicians and scientists use to analyze change and accumulation, setting the foundation for many modern applications. Understanding their contributions helps us appreciate how these mathematical tools evolved and became essential in various fields today. In the business world, derivatives have a wide range of practical applications. One of the most important is when data is organized visually, like on a graph or in a data table, such as in Excel. Once you've input your data, you can create a graph to visualize it clearly. Using derivatives in this context allows you to analyze the graph and estimate key points, like where profit or loss occurs. For example, by finding the slope of the tangent line at a certain point, you can determine whether your business venture is gaining or losing momentum at that stage. This capability is especially useful for making informed decisions quickly, as it helps you identify critical thresholds and optimize outcomes. Ultimately, understanding how derivatives apply to business data connects to our broader theme of leveraging mathematics to make smarter, data-driven decisions in real-life situations. In most automobiles, you'll find an odometer and a speedometer. These are essential tools that help drivers keep track of their speed and the distance they've traveled. The odometer shows the total miles or kilometers driven, while the speedometer indicates how fast you're going at any given moment. Now, in traditional mechanical gauges, These rely on physical parts and mechanical linkages. But today, many cars use electronic versions of these gauges. These electronic systems process signals sent from sensors on the tires, which measure how fast the tires are spinning. What's interesting is how these electronic gauges transform that data. They use derivatives, which essentially means they calculate the rate of change of the tire's rotation to determine speed. And from that, they can accurately display your current speed in miles per hour or kilometers per hour. This connection between the raw data from the tires and the display on the dashboard highlights how derivatives play a crucial role in converting physical signals into meaningful, real-time information for drivers. It's a great example of how calculus concepts are integrated into everyday technology, connecting back to our overall theme of how derivatives help us understand change and motion. Now, let's take a look at how mathematics, particularly physics, play a crucial role in various fields and sciences. For example, derivatives are fundamental tools that help us understand change and motion. In physics, derivatives are used to analyze velocity and acceleration, giving us insights into how objects move over time. But the applications go beyond physics. In engineering, derivatives help optimize systems and improve designs. In economics, they are essential for modeling cost functions and maximizing profits. And in biology, derivatives assist in understanding rates of change in populations or the spread of diseases. Overall, the concept of derivatives bridges mathematics and real-world applications, making it a powerful tool across many disciplines. This highlights how mathematical principles underpin scientific discoveries and technological advancements, connecting back to our broader theme of the importance of calculus in understanding the world around us. Now, in physics, when we talk about the displacement of a moving body, the derivative of that displacement with respect to time is what we call velocity. Essentially, velocity tells us how quickly and in what direction an object is moving. If we take that a step further, the derivative of velocity with respect to time gives us acceleration, which describes how the velocity itself is changing over time. This leads us to an important principle known as Newton's second law of motion. It states that the derivative of the momentum of a body, that's mass times velocity, is equal to the force applied to it. So, in simple terms, the change in an object's momentum over time is directly related to the force acting upon it. All of these concepts, displacement, velocity, acceleration, and force, are interconnected through derivatives, which help us understand how objects move and how forces influence that movement. This ties nicely into our overall theme of understanding the fundamental laws that govern motion in physics. Let's talk about some important applications of derivatives in mathematics, starting with concavity and curve sketching. This involves understanding how the second derivative helps us determine whether a function is concave up or down, which in turn assists us in sketching the graph more accurately. Next, we have the mean value theorem, a fundamental concept that connects the average rate of change over an interval to the instantaneous rate at some point within that interval. It's a powerful tool for analyzing the behavior of functions and proving various properties. We also look at the extreme values of functions, which are the maximum and minimum points. Identifying these points is crucial because they often indicate important features of the function, like peaks, valleys, or boundaries. Overall, derivatives are most commonly used in mathematics to study the behavior of functions, how they increase, decrease, and shape their graphs. These applications help us understand complex functions more intuitively and are essential in both theoretical and applied mathematics. All right, let's look at this slide. When a function f has a constant value, meaning it's just a flat line at some value c, the derivative of that function with respect to is 0. In other words, if fx equals c, a constant, then the rate of change, or the slope, is 0 everywhere. For example, if y equals 3, which is a constant, then y prime, or the derivative of y, is 0. This is what we call Rule 1, the derivative of a constant function. It's a fundamental rule for differentiation because it tells us that constant functions don't change, so their slope is always zero. This rule fits into the bigger picture of differentiation because it helps us quickly identify the derivatives of constant functions without any extra calculation. So, whenever you see a constant function, remember that its derivative is simply zero. It's a simple but crucial concept as we build up more complex rules for derivatives. Let's look at the example f. X equals 4x cubed, which is the derivative of x to the fourth power. Now, recall the general rule for derivatives of powers. d/dx of x to the n equals n times to the n minus 1. This is essentially the power rule in calculus. For instance, if n is an integer, we might have x to the fifth, or 2 times x to the eighth, or even 3 times x to the negative third, or 5 times x to the 1/2. The power rule applies to all these cases, making it a very useful tool. In simple terms, the power rule tells us that when we're differentiating a variable raised to any power, we multiply by that power and then subtract 1 from the exponent. It's a straightforward but powerful rule that simplifies finding derivatives of many functions involving powers of x. So whether the exponent is positive, negative, or fractional, as long as it's a real number, this rule helps us quickly compute the derivative without much hassle. It's a fundamental part of mastering calculus, especially when dealing with polynomial functions or other power functions. The product rule is a fundamental rule for differentiating products of functions. It comes from the limit definition of the derivative and helps us handle situations where one function is multiplied by another. The key idea is that if both functions, u and v, are differentiable at a point x, then their product, uv, is also differentiable at that point. The rule itself states that the derivative of the product, d/dx of u times v, is equal to u times the derivative of v plus v times the derivative of u. This rule is essential because it extends our ability to differentiate more complex functions built from simpler ones, and it ties back to the overall theme of understanding how functions change. Remember, the most important part is that the derivative of a product isn't just the product of the derivatives. It involves both functions and their derivatives in this specific combination. Now, let's talk about a special rule for finding the derivative of a quotient of two functions. This is called the quotient rule. The key idea here is that if you have two functions, u and v, and both are differentiable at a point x, and importantly, if v at is not 0, then the quotient u divided by v is also differentiable at that point. The quotient rule gives us a formula to find the derivative of this quotient. It states that the derivative of u over v is equal to v times the derivative of u minus u times the derivative of v, all over v squared. This rule is really important because it helps us differentiate ratios of functions efficiently. Remember, the main points are the conditions for differentiability, namely, that both functions are differentiable and that v is not 0, and the actual formula itself, which involves the derivatives of both functions and their original forms. Connecting this to the overall theme, the quotient rule is a powerful tool in our calculus toolkit, allowing us to handle more complex functions that involve division. So, mastering this rule will definitely help you analyze and differentiate a wider range of functions with confidence. All right, let's talk about the chain rule. This rule is really important because it helps us find the derivative of a composition of two or more functions. Think of it as a way to break down a complex problem into simpler parts. The formula is di/dx equals di/do times do/dx. Essentially, we take the derivative of the outer function with respect to the inner function, and then multiply it by the derivative of the inner function with respect to x. This rule is fundamental because many functions we encounter are made up of simpler functions combined together. Understanding the chain rule allows us to handle these more complicated derivatives with confidence. It connects directly to what we've learned about derivatives so far and expands our toolkit for tackling a wide variety of problems. And finally, on this last slide, I want to emphasize that derivatives are truly a fundamental part of our daily lives. They help us understand how quickly things are changing, whether it's in business, science, or other fields. By grasping the concept of derivatives, we gain powerful tools to analyze and make decisions based on change. Remember, whether you're tracking market trends or studying physical phenomena, derivatives are always there working behind the scenes. They connect directly to the core idea of understanding change, which is central to many areas of knowledge and practical applications. So, I hope this presentation has given you a clearer picture of what derivatives are and why they matter so much in our world.